Right, this is section C of the January 2021 paper. Okay, we'll start with question 14, going to the end of the paper, which I believe is going to be question 21. Starting off with multiple choice, we've got the question: identify the material that is used as an electric insulator and can be polarized by an applied electric field. Straight off the bat, I can eliminate composite. Okay, not all composites will do anything specified in there. Okay, just by knowing a couple of composites such as concrete. All right, we know concrete can't be polarized, therefore it can't be that. Magnetic, well, nothing to do with magnetism in the specification here of this material, so we're left with between smart and dielectric. Okay, smart materials, well, I'd be looking for something to say that the physical properties or the properties of the material will change due to an external stimuli. This is oddly specific to electrical and electric field. Now, I know dielectrics are using capacitors, therefore I'm swaying towards dielectric for this particular answer. Okay. Right, question 15. Question 15, identify the electronic component represented by the symbol. Right, already I can see that there's a play button, that diode that I'm looking for. However, it's not a normal diode because we've got this line and this line here. Okay, but I'm looking for a derivation of diode in my answer. Phototransistor, no. Trim capacitor, no. Motion sensor, no. Zener diode. Okay, so just by looking at the fact that it looks similar, okay, it's probably going to be a derivation of, and therefore Zener diode is going to be my answer for that one. Okay, so that's 2 marks done on the multiple choice. Let's move on to question 16. Question 16, a 3-volt DC battery is connected to 32 ohms resistor in series. Right, okay. Well, the fact that it's in series doesn't really matter. Not too much of a problem here. Trying to calculate power. Okay. Bless me. Right, so if I'm looking for power, I'm probably going to go straight to the first page of the electrical theory and look for the power formulas. I've got P equals IV, I've got P equals I squared times by R, I've got P equals V squared over R. I've got voltage, I've got resistance. I'm going to be using that last one over here. P equals V squared over R. P equals V squared over R. Right. Simply substitute my values in, and that's going to calculate my power. 3 squared over 32. That's going to be 9 over 32, but might as well just chuck it in a calculator. See what my fraction truly is. 9 over 32 is equal to 0.28125. Okay. 0.28125, and that's going to be my power dissipated by the resistor. So quite simply, 0.28. Leave it as that. I'm just going to go give the full thing because an exact value doesn't continue on forever. And I'm going to put watts. Okay. Right. Moving swiftly here. Question 17. The diagram shows 2 charged conducting plates with a potential difference applied across them. This is essentially what a capacitor is. Okay. We've got a distance, we've got a potential difference of 12. Calculate the uniform electric field strength between the 2 plates. Give your answer in appropriate units. So, because I know it is a capacitor of sorts, I need to probably look in the capacitor section. In fact, no, it's going to be in the, is it? Ooh, I might be a bit lost. Where would it be? We're looking for uniform electric field. I'm struggling to see a formula here. Ah, there we go. Uniform electric field, the field strength. Either force over charge or voltage over distance. Okay, and it literally says here for uniform electric fields. So the formula booklet is literally giving you the answer. Unfortunately, this was in the magnetism and electromagnetism section. Okay, so do make sure that you do have a quick look through your formula booklet, familiarise yourself before the exam. Okay. These formula booklets really have not changed much at all since they were being used in 2017. Okay, so expecting everything to be the exact same for your exam. Right, so we had the voltage over the distance. Now, that's going to get us a electric field, a uniform electric field strength, which is the formula. What I need to do here is I need to convert this into SI units. Okay, so 5 mil is going to be 0.005 meters. I've got a potential difference of 12. Okay, so it's going to be 12 over. Oh, sorry, let's go to the camera. 12 over 0.005. Chuck out a calculator, figure out what we get. 2,400. Okay. 2,400 right there. Oh, sorry. Says give your answer in an appropriate units. Well, I had a voltage. Okay, I had a meter. So I could do volts, meters to the -1. Okay. That would suffice. Oh, sorry, you didn't see what I did there. I just checked voltage. Let's send the camera so it's straight. Voltage divided by meters. Okay, that's one answer you can use there. Okay, and that was for question 17. You could potentially have other answers, other units. Okay, if you weren't using proper SI units, you could have stayed in the millimeters, and you could have done volts with millimeters there. You could have changed it to kilovolts if you wanted, just for the sake of, I don't know why. Okay, but point being, as long as you've got the correct units there, you can have whatever numbers you want, provided that you've done the correct conversions. Right, explain one advantage of using a stabilized power supply when prototyping electronic circuits. Right, if you're prototyping electronic circuits, you're probably trying to figure out what components you can get away with, and the likelihood is some of the components can be delicate. So, by stabilizing the power, you can make sure that the voltage is going to be constant, and therefore you're not going to have too high a voltage and just essentially fry your delicate components. So, delicate components won't get damaged, provided there is a constant voltage. Okay, delicate components won't get damaged provided there is a constant, I can't spell constant, a constant voltage from the stabilized power supply. Explain one advantage of using a stabilized power supply when prototyping. Delicate components won't get damaged provided there is a constant voltage from the stabilized power supply. So I've stated exactly what's going on. I've relayed it back to the question. Stabilized power supply, you should have a constant voltage and therefore your delicate components won't get damaged, okay? I just wrote that in reverse order, but you could write it in whatever order you want, provided that your sentence just does make sense. This should be sufficient for 2 marks, okay? I would always recommend with these explain questions, refer back to your textbooks, double check with what they say in textbooks, because after all, you're trying to communicate with an exam board. It's best to communicate with an exam board in the language that they expect, okay? So you might as well have a quick read of your textbook, see how they've stated this. Try and memorize it, give it back to them when the time comes in the exam. Okay. Right, a single phase AC power supply. Straight away, I'm going to turn to my single phase alternating current theory. Okay, at the bottom here, just at the bottom here, this set of formulas. Right, it's asking for an RMS voltage of, at a supply of RMS voltage of 230. Calculate the peak value. Right, so I'm looking for the root mean squared voltage formula, which is RMS is equal to peak over root 2. Therefore, rearranging for the peak value, we're going to have RMS times by root 2 equals peak. And therefore, 230 times by root 2 is going to equal 230 root 2. And therefore, our peak value, let's grab the calculator, 230 root 2 equals 325.269. Just double check, I just put not a plus 8 times in there. Yeah. Okay, 235.269, that's going to be a peak value of voltage. And I'm going to write that on my answer line. 325.27, rounded, 2 decimal places, voltage. Calculate the average voltage, the average value of voltage for the power supply. We've got a formula in here. Now, this formula refers to either voltage or current, depending on what the question is, but it's asking for the waveform average value. Okay, if you're putting in the max value of, say, voltage, okay, which is, in other words, the peak value, okay, then you're working out the average voltage. If you do the same thing for current, maximum currents, then peak current, you're going to be working this out. Okay, it applies the exact same thing because it's on a sine curve. Right, with all that being said, let's go about and use that formula. Let's write it out first of all. AVG, average, is equal to 2 over pi times by peak. Peak is this value that we've got over here, which fortunately I've got saved in my calculator. So I'm going to rewrite this down over here. 2 over pi times by 325.269. Right, all I'm going to do is I'm going to take my answer that I've got there, I'm going to just press times. So my answer is still 325.269. Okay, times it by the fraction 2 over pi. Whatever my value is going to be my average. 207.0727527. That way I've got the exact value. Alright, no rounding error there. So now I can round it. I'll go 2 decimal places again. 207.07. Alright, this is going to be average value in volts once again. So let's chuck this at the very bottom of the page. 207.07 volts. And that's that question dealt with. Moving on to question 20. Okay. Question 20. Diagram shows a coil with 120 turns wrapped around a former. Okay, so we're looking at a solenoid here. The coil has a relative permittivity, mu r of 200. Okay, current is 1.5 amps, flows through the coil, calculate the flux density of the magnetic. There's a lot going on here. I say there's a lot, 6 marks, so potential 2 formulas, maybe 3. Right, let's figure out what we're trying to calculate, and let's work backwards using the formulas that we've got here. Fortunately, when it comes to magnetism, there are no formulas hidden. Okay, everything that we need is given in the formula booklet, but we might need to appropriate some formulas, especially if we're dealing with mu r. Okay, because we aren't given the fact that mu r times by mu naught equals mu. Okay, so that's the only thing we've got to worry about, but that was a lot earlier on than magnetism. Okay, right. Flux density of the magnetic field around the coil. We're looking for magnetic flux density, which is B equals this symbol. Can't remember what it is. Over A. Just seeing if we could see the formula elsewhere. Oh, it's evading me. Either way, doesn't matter too much. We're trying to get the flux density here. Okay, which is formula going to be B equals that over A. That's what we're trying to solve for. Here's the issue. We don't have anything to do with area. And we can't figure out what area is because there's no other additional information. So I'm going to have to use a different formula, which is B over H equals mu naught mu R. Right. That we do have a lot of information for. Okay. So we need to use the formula B over H, equals mu naught mu R. Right, the thing that I'm looking for now is how do we solve for H? Okay, if we try and solve for B, and we've got mu naught because it's in the formula booklet as a value of permeability of free space times by the relative permeability. So we've got this, and we're trying to solve for B. We also need H. So I'm looking for my formula booklet here for H. H is given here, which is H is equal to N, which is the number of turns, I, which is the current which you got, and L, which is the length which you got. So fortunately we can calculate all of this, therefore we calculate H. Because we can calculate H, we can calculate B, which is the thing that we're trying to solve for. I'm going to get rid of this formula here, considering we can't use it. Right, now it's just a matter of making sure all our numbers are in SI units, and just simply doing the calculation. I've got N. N is going to be the number of turns, so 120 times by amps, which is 1.5 in SI units, lovely stuff, times by the length, which is 0.1 meters, once again in SI units. This is going to be 18,000. Let's just do this in the calculator so that you can have a bit of confidence in me. Oh, sorry. Let's put some brackets, and that way I can quickly cheat with the fraction. There we go. So 120 times by 1.5 over 0.1 should be 1800 or 1800. There you go. And that's going to be the value for H. With that being said, I now need to look at this formula and rearrange it. We're solving for B, and that's going to have to equal times both sides by H, therefore H, times by mu naught, which we can find in the formula booklet in a moment, times by mu R, which we do have, that's 200. Let's substitute all the values in that we've got so far. B equals H, which is 1800. Right, let's go to our formula booklet and let's find our value. It should be on page 3 where we're given the other two values, one being gravity, one being permittivity. Right, here we go. Physical constraints, acceleration due to gravity, G. Permittivity, and we're looking for permeability. Permeability is 4 pi times by 10 to the minus 7. So and then mu r is 200. Okay. Now something to be said, especially if we're running the Casio calculator I'm running here, you can't do 4 times by pi times by 10 to the minus 7 with the standard button down here. Okay, I'd recommend you put these in brackets, you times them together to get the actual value, then you do that times by 10 to the minus 7 there, because for whatever reason when you do that with pi you just get a syntax error. Okay, fortunately we've got everything we need. Okay, all I'm just telling you is to bracket this stuff so then it doesn't bug out. Times by brackets for pi, close brackets, times by 10 to the minus 7, okay, times by the 200. Let's see if this works. Nope, syntax error still. So syntax error, so it's still not happy with this value here. Yeah, okay, so here's what I'm going to do. I'm going to do 4 times by pi. Gets me an answer with that. I'm going to do answer times by 10 to the minus 7. See if this works. Nope, still not happy. This is proving to be a bit annoying. Right. How else would we be able to get around this? Okay, I'm just going to have to do it the standard way. Let's go 1800 times by 4 times by pi times by 10 to the power of minus 7. Okay, so I'm going around it by not using this button, I'm going around using the traditional way. Times by 200. Oh, sorry. Don't want that. Times by 200. Okay, so we've got to be really careful here, considering that the calculator is being a bit annoying with the issue of using a symbol. You can't use times by 10 to the minus 7 as a feature. There we go. BI is going to equal 0.452 389, so on and so forth, but we don't need that many decimal places. Let's just go to the first 2 decimal places. I'm going to give it as b equals 0.45. 0.45. Okay. Right. Oh, sorry. I've placed that on the answer line just down there. Right, and that's that question 20 dealt with. Okay, so it is possible your calculator just might be a bit annoying when you go to answer that question. Right, let's have a quick look. Capacitor, already looking at this question, series circuit, capacitor involved, AC, supply. Immediately I'm looking for a few formulas here. Okay, I'm probably going to have to deal with total impedance of a capacitor equation in a series with a resistance. Let's have a quick check. Do we have a resistor in the question? At the top, 56. Yes, I'm going to be using that formula. Okay. I like these questions because they can only ask it one way. And quite frankly, you don't actually need to be a genius to figure these out. You just need to know whether you've got an inductor and a capacitor. And from there, the formulas sort of just fall into place. I will do my best not to explain this question fully, but just use the formulas and convert stuff that I need to. Okay. Right. We've been asked to calculate the frequency frequency. Okay, so frequency is the letter F. Now, there's potentially two formulas I could use. It's either capacitive reactance or inductive reactance. Now, if it's inductive reactance, I should have an inductor. Okay, an inductor, but I don't, so I've got a capacitor, therefore I'm going to be using this one up here. Okay, so F is the thing I'm trying to solve for. I've got the formula. XC is equal to 1 over 2 pi FC. So already I know I'm going to have to rearrange this equation later on. I've got pi, I've got 2, I've got 1. Do I have XC? No, I don't have any information for XC. I do have the capacitance though. So I need to find a formula that's going to calculate XC for me. There is another formula over here for the total impedance of a capacitor, which uses the formula Z equals XC squared plus R squared all over, all under the square root there. That's impedance. Do I have impedance? No, I don't. So now I need a formula for the letter Z. Well, fortunately, Ohm's law AC circuits includes this formula, which is the current is equal to the voltage over impedance. I do have a voltage, I do have a current, therefore I should be able to work out the impedance. If I've got the impedance, I should be able to work out what XC is in this calculation over here. Once I've worked out XC, I can then filter into here. So, right, I've got all the formulas I need because each formula only has one variable missing. And this is the one that's going to solve everything for me. Starting with, let's solve for Z. I'm going to swap these about. It's going to become Z equals V over I. Moving down a bit further, I'm going to have voltage being 60 over the current, which is 0.16, equals Z, which happens to be equal, let's chuck in a calculator, 60 over 0.16 equals 375. This is impedance, therefore it's going to be in ohms. Okay, I've got Z equals 375. Let's now go over to this formula over here. Right. What I'm going to do is I'm going to substitute my values in this time, then I'm going to rearrange after. Okay. 375 is equal to square root of XC squared plus the resistance, which is going to be 56 squared. Sorry, I didn't mean to write the 2 there, I meant to write the 2 up there, but not subscript, I wrote superscript because that was the value that's going to be squared. Right, I've got these values in play. I'm now going to rearrange. I'm going to square both sides, which is going to get rid of the square root, therefore that's going to be squared. And then I'm going to subtract by 56 to get it over to the left hand side. In fact, what I'm going to do is I'm going to do this part step by step. 375 squared is equal to XC squared plus 56 squared. Subtract the 56 squared from both sides. 375 squared minus the 56 squared equals XC squared. I'm going to square root both sides. And that's going to be 375 squared minus 56 squared square rooted equals to XC alone. Therefore, XC can then be placed into this formula over here, and we can do all of that now. Formula is pi square root 375 squared minus 56 squared equals to 370. XC equals 317.7 950917. Okay, that equals this over here. Instead of substituting in everything first time around, I'm going to rearrange for f, and then I'm going to place everything in because I want to try use the answer that I've got over here in one foul swoop. So first things first, I'm going to times both sides by f, divides both sides by xc. So f is equal to 1 over 2 pi xc times by c. Okay, 1 over 2 times by pi times by xc. xc was just 370.795 times by capacitance, which was given in standard units as well, which is even better, which is 32 times by 10 to the minus 6. Fortunately, in this one, we will be able to use our standard times by 10 to the whatever button, due to the fact that we're not timesing by a symbol. We've got 32 there. Okay. Right. Apologies, I nearly broke something. Right. I'm going to put the fraction in. 1 over 2 times by pi times by answer, yep, times by 32, which is going to be times by 10 to the minus 6, equals, we're looking for frequency, which is f, and all of this is going to equal 13.41331664. In other words, it's just going to be 13.41 hertz, Hz. 13.41, oh sorry, you can't see that. 13.141 hertz. Right. That is everything for this 10 marker. So, if you have any questions, please leave a comment in the comment section and I should get around to you. But other than that, that's it for this video. I'll see you in the next one.